Okay, so all the stuff you've recently forgotten over the break, okay, that we talked about on Wednesday and Thursday, I will quickly review here. Okay, the big thing is scalars and vectors. All right, we talked about how some things give us just a magnitude or a measurement, and other things give us a measurement or a magnitude and direction. All right, if we are talking about a scalar quantity, okay, a scalar quantity gives us only a measurement, only a magnitude. All right, so things like distance are scalar. All right, it tells me how far something is from something else along whatever path I take to get there. All right, so we could say that Calgary is 40 kilometers from Okotoks. Okay, and we'd be right in that. That's about how far we would have to drive to get to the center of Calgary from the center of Okotoks. Okay, it doesn't give any reference to what direction we travel, just how far we would have to go. And part of the reason it doesn't tell us what direction we go is because we go several different directions. Okay, we make all kinds of turns and adjustments along the road that gets us to Calgary. Okay, but in the end, we will travel 40 kilometers in getting there. All right. A vector description of that trip would be our displacement. And our displacement would be a smaller number because it would be a straight line. Okay, so it would be represented by that line instead, which would be less because the shortest point between shortest route between 2 points is a straight line. So this would be, let's say, probably not 40 kilometers, but we might shave off maybe 5 or 6 kilometers off of that. So maybe it's 35 kilometers. Okay, and now it's 13 degrees east of north. It doesn't really look like that, but let's say it is. Okay, it would actually be 13 degrees west of north, not east. Okay, how do I know it's west of north? Because it's a little bit west of north. This would be north. Okay, that would be straight north. This is a little bit west of it. Okay, about 13 degrees or so. All right, so that's giving me a vector description. It isn't any more accurate than the distance was. Okay, but it does give me an extra piece of information, right? And that is what direction I would have to go if I could actually physically travel in a straight line from the center of Okotoks to the center of Calgary. All right, now the only way I'd be able to do that is if I had what? Well, not a plane unless you want to land it like that person did last year on 32nd Street there in the Northeast. Okay, it was an incredible piece of flying, make no mistake, but I don't think you'd want to repeat the process in downtown Calgary. If I had a helicopter, it might be a little easier, right, because I can take off vertically. But I certainly couldn't walk that straight line because I'd have to walk through trees and buildings and people's houses and stuff, and that might be awkward and difficult and impossible. So, okay, that just tells me, okay, the vector description of this, or the displacement, is telling me how far and in what direction I end up, not actually that I would travel that way, but how far I would end up from my starting position. All right, so one is just giving me the number, okay, and the other is giving me the number and the direction. Okay, speed and velocity work the same way. Speed is a scalar description of how fast you are going. Right? So if you get pulled over by the police, okay, and they say, how fast are you going? Tell them how fast you're going. Give them your speed, not your velocity. All right, because if you say to them, I'm going 125 kilometers an hour at 13 degrees east of north, they will follow up with another question. And how much have you had to drink today? Okay, probably not the line of questioning you want to have them doing, okay, while you're driving. So, yeah, just give them your speed. They don't care what direction you were going, unless, of course, you were going 125 kilometers an hour in the wrong direction on the Deerfoot. That's an entirely separate charge, okay, and you probably have bigger fish to fry if that's going to apply to you, okay. They're only caring about the scalar quantity, your speed. How fast are you going? Nobody gets a velocitying ticket, okay. They get a speeding ticket. You were going too fast. Okay. All right, then we looked at this example here, okay, the trip from my house to Walmart, and we said I would probably have to follow the squiggly line in order to walk to Walmart, okay, which would mean I would travel about 4 kilometers. And we said that would take me about a half an hour. Right? So if we wanted to calculate my speed, what we did is we took this formula right here, and we said that v, which is my speed, is calculated by taking my distance, 4 kilometers, and dividing by how long that took me, a half an hour. Right? When I did that, I found out that my speed was 8 kilometers per hour. Right? If I wanted to calculate my velocity, then I would need to know my displacement. My displacement is the straight line, right? And we said that my displacement would be 2.7 kilometers at 30 degrees south of east. So here's that 30 degrees, okay? This dotted line here is due east, so obviously I went south of that, okay? So I've got my 2.7 kilometers, 30 degrees south of east. It's the same trip, so it took me the same time. It was still a half an hour. So now my velocity, which is a vector quantity, is 5.4 kilometers per hour at 30 degrees south of east. Notice that when I divide these things, my units get divided, so I have kilometers divided by hours. And since there's nothing to divide my direction by, my direction remains the same. Okay? In fact, my displacement and my velocity will always have the same vector because they're talking about the same trip. They have to point the same way. Okay? It would be impossible for me to displace myself 20 kilometers east by walking at 20 kilometers an hour north. Okay? I'm just never going to end up east by doing that. All right? So my velocity and my displacement are always going to share the vector. And it's always going to be the same. Everyone all right with that? All right. So those were the two formulas that we talked about. Now, here was the thing about scalars and vectors. When we talked about this, I said, I forgot my wallet. And I didn't realize that until I walked right up to the door of Walmart. Since I don't like going into Walmart even if I have my wallet, I'm certainly not going in there if I don't have it. So I turned around and walked all the way home along exactly the same path. Now, what's my total distance? 8 kilometers. All right, and now I've been walking for an hour. My speed is still 8 kilometers per hour because now I've actually walked 8 kilometers in 1 hour. But from a vector perspective, I am now back where I started from, which means my displacement is now 0 because displacement measures how far and in what direction I am from my starting position. And according to that, I'm now back where I started, so that distance is, or that displacement is 0. I have not displaced myself from where I went, or from where I started. Okay, so even though I've walked a total distance of 8 kilometers, I ended up back where I started and have not displaced myself at all. Everyone okay with that? Okay, so now, over the whole trip, there and back, what's my average velocity? Right, 0 kilometers per hour. Remember, velocity, according to this formula, is displacement divided by time. And I just said my displacement, now that I'm back at home, is 0. 0 divided by anything is 0. Okay, everybody all right with how that works? Okay, so that's kind of where we left off there before the break. So, wording here, I think I changed this in your notes package. It doesn't say more accurate. In yours, it says a more descriptive description here. Okay, and that is a vector measurement, okay, or a vector quantity is not necessarily more accurate than a scalar quantity. Accuracy comes from how you measure it, not what you're measuring. Okay, distance and displacement measure slightly different things. One measures how far you go, the other measures how far and in what direction you are from where you started. Okay, if I measure those with the same instrument, they are going to be equally accurate. However, if I measure one of them with a meter stick that has no increments on it, I can only be accurate to how much? A meter, right? If this has no markings on it, all I know is that it's a meter long. If I measure that distance, I can be accurate to plus or minus one of these, and that's it. If I use this one instead, okay, which is accurate to the nearest millimeter, okay, I'm now going to be measuring much more accurately. Okay, so it would be possible, okay, for me to say, sure, my displacement is 40 kilometers, 13 degrees east of north, but, okay, my distance traveled was 40.000 kilometers. Which one of those is more accurate? Yeah, this one. Even though it's a scalar quantity, it's more accurate because I measured it more accurately. Okay, so accuracy comes from measurement, not from what information you are given. Okay. All right. just difference here again, and I've said this a bunch of times today, but just so we have it on paper, okay? Distance tells us how far an object travels, okay? And displacement tells us how far and in what direction it is from its starting position. So we need to make sure that we recognize those are two different things. So d is distance. D with the arrow over top is displacement. Okay? Anything with an arrow over top of it is a vector quantity. Okay? So the same is true for speed. V with no arrow over top is speed, because speed is scalar. V with the arrow over top is velocity. Right? And we've got lots of other vector quantities, okay, that we deal with in physics. Okay, another one that we'll deal with in physics here in Science 10 is acceleration. Okay, so it'll be an A with the arrow over top of it. Right? One that we'll deal with in Physics 20, but not in Science 10 so much, is force. Force is also a vector quantity. That's supposed to be a C. Okay, so it's got an arrow over top of it as well. Yes. Okay. E, on the other hand, represents energy. And energy is scalar. Okay? It doesn't have a direction, so it doesn't get an arrow over top. All right, everyone follow the convention there? Okay, so speed and velocity then have a similar relationship. Speed is the scalar version, just tells people how fast I'm going, whereas velocity tells me how fast and in what direction from my starting point I am headed. All right, so then we'll come up with this part here, which we've already talked about. If I travel home along the same route, okay, then my displacement will be 0 when I get home. And I think we talked about the example of that's why the odometer in your car reads the distance you have driven your car and not its displacement. Okay? Otherwise, whenever you came home, it would always read how far it was from wherever it was purchased. Okay, because it would always read displacement, which is not useful. Okay, ringing a bell. Okay, algebra. This is not algebra. You may not ever use a triangle in my class to do algebra because it won't work. Okay, it's not going to work. It works fine for a formula like V equals D over T. It works fine for the mole equation where you've got 3 variables and they're only being divided or multiplied. Okay, then it will work. As soon as you get into a formula that has more than one type of operation, so it has multiplication, division, and addition, subtraction, doesn't work. Okay, has more than 4 variables, doesn't work. Okay, all of those kind of things. And I've had people say, well, then there's got to be a shape for it. I'm like, okay, fine, go ahead and find the trapezoid that works for that formula, okay, or whatever. You're not going to. Okay, the easiest thing to do here, guys, is just to learn the 3 simple rules of algebra for manipulating a formula. Okay, so if I want to manipulate V equals D over T to solve for D, what should I do? I want to get D by itself. Okay, so I got to move T, all right? And if I want to move T, I'm going to multiply both sides by T because right now I'm doing what with T? I'm dividing by it. And if I want to move something, I do the opposite. That's the first rule of algebra. Okay? If I want to move something, I do the opposite operation. So essentially, I just take T and I multiply both sides by it. Now D is by itself, and I'm solving for D. All right? Now, what I've effectively done by doing that is this. Okay, so I've said, all right, I'm going to multiply this side by T. So I have a T on the top and a T on the bottom, and thus they cancel. Okay, and then I multiply this side by T because the second rule of algebra says whatever I do to one side, I have to do to the other. There's your 2 most important rules of algebra. Okay. All right, so that's the second rule of algebra. Okay, what I do to one side, I do to the other. Now, the third rule won't apply to this formula. Okay, I don't have to worry about the third rule in this formula, but I'll show you one that we will have to use it in here in just a second. All right, so what we're going to do, what if I want to solve for t? Okay, if I divide by d, which is a way to do it, what am I going to be left with? 1 over t. Okay, if I divide both sides by d, all right, so I divide this, what's d divided by d? 1. Okay, so yeah, the d cancels, but it leaves me with a 1 here. Then I can divide this side by d, but am I solving for t then? I'm solving for 1 over t, which is not the same thing. Okay, that would be like saying 5 is the same as 1 over 5. Is it? No, it's definitely not. All right, so what I would want to do instead is multiply both sides by t so that t goes to the top of the equation. Now, I want t by itself, so what do I do with v? Divide both sides by it, right? Now I'm solving for t. Okay, all I've done is follow those two rules that we talked about. Okay, if I want to move something, I do the opposite, and what I do to one side, I do to the other. Right? That's all I've done thus far. Now, one thing that is sometimes a good idea, if you're not sure of your algebra, is to check by looking at the units you would get. All right, so if my distance was in kilometers, okay, and my speed was in kilometers per hour, okay, and I divided those, what would I be left with? Hours. Is that a unit for time? Then I probably manipulated this right. Okay, there's always a way to double check. If you're not sure, you can do what we call a unit analysis to see if you get the right units for what it was you were looking for. Okay. Same thing would work if I was solving for d. Okay, so if we go back to that idea here, okay, solving for d, I would take my hours, okay, multiply it by kilometers per hour. Okay, I got an hours on the top, hours on the bottom. I'm left with kilometers. That's a unit for distance. I probably manipulated it correctly. Okay, everybody all right with that? Now, the third rule of algebra will come into play, okay, when I'm manipulating equations like these. For right now, we'll ignore those ones. Okay, but we'll look at this one here. Y equals mx plus b, because we'll be dealing with this later on this week. This is the graphing equation. How many people have seen it in math already? Good. Okay. If I want to manipulate this equation for m, how do I do that? How do I get m by itself? Okay, there's an order in which I have to do this. Yeah, okay. I need to subtract b first and then divide by x. Okay, that's the third rule of algebra. The third rule of algebra is move what's not attached to what I'm looking for first. Okay, it's kind of like following order of operations in algebra. Right, so I would move the b first and then I would divide by x. Right, so here are our three rules of algebra. You should probably write them down. Okay. All right, the golden rules of algebra. Rule number 1, okay? Okay, to move a variable, perform the opposite operation. So if whatever it is you're moving is being added, you would subtract. And if it's being multiplied, you would divide. Okay, the second golden rule of algebra is, okay, is to perform that operation on both sides. Okay? And the third golden rule of algebra, okay, is when you're isolating something, move what's not attached first. All right, so if we're looking at the graphing equation and I want to solve for m, I'm going to move b first because it is not attached. Okay? To move b, I'm going to perform the opposite operation. Right now I'm adding b, so I'm going to subtract b from both sides. And what I'll end up with is y minus b equals m times x. Okay, so far I've followed all the rules. I moved what wasn't attached. I did the opposite operation to both sides. Now I want to get m by itself. M is being multiplied by x. So to move x, I need to divide by x, right? I'm performing the opposite operation. The opposite of multiply is divide. Okay, so y minus b divided by x will give me m. Right? All I have to do is remember those three rules. Those three rules will be good enough to get you through any linear mathematical course. Okay? As long as you don't get into nonlinear stuff like, calculus-based astrophysics, you'll be fine. Okay? I got through university physics on those three rules. Okay? Those three rules and those three rules alone, okay, got me through university physics, except for my calculus course, which I just memorized all the examples in the textbook and wrote them down on the final exam and got part marks for method, because I didn't understand a single thing in that course. Okay? But that was enough to get me enough marks to get me through on the curve, because it was smarter than what everyone else in the class figured out. Okay? At least I was in a class full of people that were at least as dumb or dumber than me. Okay? All right. I don't recommend that as a method for success, by the way. It just happened to work and I was desperate. All right. Everybody okay with how that works? Okay, and those three rules of algebra? Right. So we're going to look at a few kind of example problems using v equals d over t here now. Oh, and then I wrote them again. Okay, and again. All right, let's try this one. Okay, I want you to write this problem down first, okay, and then we'll walk through how we would solve it. So similar to how we dealt with mole equation problems, okay, the first thing we want to write down when we're dealing with a physics problem is the givens from the question. All right, so this question is asking how far a deer will run. How far means it's asking for what? Distance. All right, so distance is not a given, but it's one of the things in the question, and it's what I have to find. Now it says it's running at 15 meters per second. What's that represent? Speed. How do I know it's speed and not velocity? There's no direction, right? Okay, and it says that it's going to do that for 45 seconds, which is a time. Okay. Right, so I have to understand what units represent what when I'm going through an equation, so I can recognize what variable these things represent. All right, so I'm looking for d. I have v and I have t, which means I'm probably going to be using this formula, especially since I haven't taught you any others yet. Okay, so v equals d over t, speed equals distance divided by time. But I'm being asked to calculate distance. So I do have to manipulate this formula, okay, in order to get d by itself. So that means I've got to move t. T I'm dividing by right now, so if I want to move it, I'm going to multiply. All right, so I multiply both sides by t, it cancels over there and comes over here. T times v equals d. All right, now that I've done that manipulation, I can plug in my numbers. 45 seconds times 15 meters per second will give me d. Okay, so we're looking at a deer that will run 675 meters. Okay, and I can't put a direction on that because it's distance, it's scalar. I wasn't given any directions in the question, so that's what I have to leave it as. Well, deer are pretty fast. Like a person, a well-trained like athlete could run 480, 490 meters in, well, it's probably not that much. Let's say closer to 400 meters in about that same time. Okay, deer are fast. Okay, like if a deer really wanted to run away from you, you'd have no chance of catching it. Okay. All right, everybody okay with that one? All right. Then I want you to try this one. This one's asking how long it will take for a tortoise to crawl 200 meters at a speed of 0.25 meters per second. Okay, give you a minute or two on that one. So this question is asking how long something will take. So I'm looking for what? Looking for time. Okay, it's telling me that the tortoise is going to crawl 200 meters. So that's the distance. And I know it's distance because they didn't give me a direction, at a speed of 0.25 meters per second. Okay, so the formula I'm going to use again is V equals d over t, but now I'm solving for t. I want to move t over here beside v because that will put it on the top of the equation. I can't solve for it on the bottom because I'll be solving for 1 over t, and that's not the same thing. All right, so I'm going to multiply both sides by t, and then I'm going to divide both sides by v. So t will equal distance divided by speed. That'll be 200 meters divided by 0.25 meters per second, which should give me 800, right? 800 what? Seconds. All right, so it'll take the tortoise 800 seconds to go 200 meters. That's actually a fairly fast tortoise. Okay, because yeah, I mean, a person can run 200 meters in 22, 23 seconds. Okay, if you're Usain Bolt, you can run at 19 point something. But okay, yeah, the average person take over 20 seconds to do that. So a tortoise at breakneck speed for a tortoise, okay, quite a bit more time than that. All right, questions on how that one worked? Everyone's okay with that? Okay, so when we're dealing with scalar quantities, okay, it's relatively straightforward. But when we start bringing in vector quantities, then we have to start keeping track of whether something is moving in only one direction or whether it begins to retrace its steps along and go backwards. Okay. So this is going to be our example vector problem. I'll give you a minute here to write it down, and then we'll walk through how to solve it. Okay, so we have a bus that's traveling 100 kilometers north in 1.2 hours, then turns around and travels 62 kilometers south in 0.9 hours. We're looking for the average velocity now of the bus. Okay, so there's a couple of things that are different about this question. First off, direction is important. Secondly, this is a trip consisting of two parts. And the other questions were, it went in this one straight line and that was all it did, right? So what we have to look at here is that this formula that we have for velocity is actually calculating average velocity, okay? It's calculating average velocity by taking the total displacement and dividing it by the total time. We never write the words total and the average part in there because it's kind of taken for granted that we understand that's what we're doing. If it's a trip with only one part, it's still the average velocity over that one part. But if we're talking about a trip with more than one part, it's also still calculating the average over all of the parts. Okay? Now, usually at this point, people look at that and go, well, Mr. Coder, like if I calculated the average, like the velocity during this part, and I calculate the velocity during that part, can't I just average the two? No, I can't. Okay, I know that up until this point, you've been taught that's how you calculate averages, and that's fine. It is how you calculate averages if all the things you're adding together represent equal parts of the whole. So like if I'm calculating a class average, you all each represent an equal part of the class. So I can add you together and then divide by the number of people. But in this case, one of these parts of the trip is much longer than the other and thus represents more of the trip than the other part. So I have to weight the average in favor of the bigger part of the trip. Okay, that's why we solve it this way and not by finding the two and adding them together and dividing by 2. Everyone follow? Okay, that would be equivalent to me doing this. I drive to Edmonton, okay, and I drive at 120 kilometers an hour all the way from Okotoks to like right up to the international airport, which is just south of Edmonton. And then I run into some construction. And for the last 10 kilometers of that 300 and some kilometer trip, I have to travel at 50 kilometers an hour. So I'm going to find my average velocity for that whole trip by going 120 plus 50 divided by 2. Okay, is that an accurate way to calculate my average? No. Okay, I traveled at 120 kilometers an hour for like 98% of the trip. It should represent 98% of the trip, not half of the trip. Okay, and that's again one of those ways our society talks about things, because when you finally got to wherever you were going in Edmonton, you go, man, for half the trip I had to go 50 kilometers an hour. It wasn't half the trip. It felt like it because it's inconvenient, but it wasn't half the trip. But our mind does that. It's like there was this part where I was able to do this, and then there was this part where I had to do this, and there were 2 halves. Well, they're not really a half. They're 98 100ths and 2 100ths. Okay, not a half. Everyone kind of follow there? Okay, so we're just making sure we're weighting it that way. So what I want to do is I'm going to write down my givens according to what part of the trip they happen in. So I'm going to write down part 1, part 2, and then I'll have my totals. Okay, so in the first part of the trip, the question says I go 100 kilometers north. So that is a displacement. Right, and that takes 1.2 hours, it says. Then in part 2 of the trip, it says that my distance is 62 kilometers, and it's south, and that takes 0.9 hours. All right. If I want to find the average velocity of the bus, then I need the total displacement over the whole trip and the total time. Can I find that? Yeah. I went 100 kilometers north, and then I went 62 kilometers south. How far did I end up from where I started? 38 kilometers north. Okay, because really, if I'm representing this trip with a diagram, I did this. I went 100 kilometers north, and then I went so this is where I ended up. Here's where I started. All right, that distance there is 38 kilometers north of where I started. That's where I am now, 38 kilometers north of where I started. Okay, so I'm going to write over here that my total displacement is 38 kilometers north. All right, what's my time? 2.1 hours. Okay, my total time is 2.1 hours. So even though I kind of subtracted the displacements, I didn't subtract the times. Because if I subtracted the times, that meant I did what? Went back in time, okay? Which I didn't do. All right, so my total time is 2.1 hours. My total displacement is 38 kilometers north. Now I can find my average velocity over the whole trip. Okay, it's going to be 38 kilometers, okay, divided by 2.1 hours. Oh, sorry, I have the answer here. It's 18.1 kilometers per hour north. Okay. So in a question like this, direction is important. right? I have to keep in mind that in one part of the trip I went north, and in one part of the trip I went south. And that's as difficult as directions will be in Science 10. We deal with what we call only one-dimensional types of motion in Science 10. Right? You're not going to have to worry about bringing in trigonometry and angles and stuff like that. We'll do that in Physics 20, okay? But not in Science 10. So yours will all be forward and backward, left and right, up and down, okay, whatever. They'll always be opposite. Okay, what if now there was a part B on this question that said, what is the average speed of the bus? Right, right. Okay, now the directions don't matter. Speed is scalar. And it wants, if I want to know the average speed, I just need to know the total distance divided by the total time. Right? Direction doesn't matter. It doesn't matter that I backtracked. Okay, the distance I travel is 162 kilometers. Time is 2.1 hours. That doesn't change. Okay, now I calculate my average speed to be 81 or something like that, or 78. So 77 kilometers per hour. Okay, no direction on that because I took a scalar quantity and divided it by time. Okay. All right. That's a very typical type of question that you might encounter. Okay. All right, so just kind of review here. Scalar quantities, they have magnitude only. Speed, okay, is a scalar quantity. Distance is a scalar quantity. Mass is a scalar quantity. Time is a scalar quantity. Okay, vector quantities, like we said, displacement, velocity. Okay, and we talked about this as well. Average speed is total distance divided by total time. Average velocity is total displacement divided by total time. Okay. Okay, give that one a try. It's pretty easy. Probably take you less than a minute. Okay, so this is about as easy as a v equals d over t problem would be. Agreed? I don't even have to manipulate, right? V equals d divided by t. The distance is 100 meters, okay? The time is 20 seconds. So 100 over 20 is 5 meters per second. Okay, everybody all right with that one? Okay, and we've done one like this as well. Okay, we'll just have a quick look at this one. How long will it take a jet? So we're looking at calculating time. Okay, traveling at 330 meters per second, which is the speed of sound. Okay, to travel 400 kilometers. Now, there's a bit of a trick to this one. What's the trick? Right. My units for distance have to match. Okay, distance is part of speed. And in this question here, I'm given the speed in meters per second, right? If I want to calculate the time, then I have to have the distance units match the velocity or the speed units. So how many meters in 400 kilometers? 400,000. There's 1,000 meters in a kilometer, so it's just multiply it by 1,000. So when I'm calculating this, I'm going to have v equals d over t. I'm looking for time, so I multiply both sides by t, then divide both sides by v. So t will equal d over v. That'll be 400,000 meters divided by 330 meters per second. All right, so we are looking at 1,212 seconds, okay, for it to do that. Okay. Now again, the ones that are only involving scalar quantities are fairly straightforward. Okay, they're not going to involve too much, taxing math or anything like that. All right, bird flies 650 meters north at a velocity of 9 meters per second north. How long is it flying for? Give you a minute on that. Like we said here, this one's basically the same as the last one, okay? All that happened in this one was I gave you a direction. Did the direction actually matter? No, it didn't, because we were looking for time, which is a scalar quantity anyway. The directions actually cancel mathematically when we do this. So we have a velocity of 9.0 meters per second north. Okay, we have a displacement of 650 meters north, and we're looking for the time. So T equals D over V, same as it did in the last one. So that'll be 650 meters north divided by 9 meters per second north. Okay, so the norths are going to go away, okay, and we'll be left with the time 650 over 9. Okay, so this is going to take 72 seconds. Okay, making sense to everybody? All right, I'm going to give you about a 4-minute break here, okay, and then we're going to just do some practice on this stuff here after that. All right, let's have a look at this one. So because this is a trip that has more than one part, so it has 2 parts, okay, we want to write down our givens part by part. Okay, so we'll have the givens for part 1, givens for part 2, and then our totals, okay, over here. Okay, so in part 1, we're displaced, and it says here 85 meters up in 30 seconds. Okay, and then in part 2, okay, it says that we go 60 meters down in 20 seconds. Okay. Now, part A wants to know the average speed. So does speed care whether I went up or down? No, speed is scalar. Okay, we calculate speed using distance divided by time, and that's total distance divided by total time to get us the average speed. So what I need to find here is my total distance. All right, my total distance is going to be 145 meters, 85 plus 60. Everybody okay with that? Oops, sorry, I put an arrow over top. That shouldn't have an arrow. This should just be D. Okay, so 145 meters. And then our total time is 50 seconds. Okay, 30 plus 20. Everyone okay with that? All right, part B wants to know the average velocity. So do I also need to know my total displacement? Yeah, because velocity is total displacement divided by total time. So if I went 85 meters up and then 60 down, then I am still 25 meters above where I started, right? So all right, so now I've got all my totals. Now I can calculate my average speed. So it'll be total distance divided by total time. So that'll be our 145 meters divided by 50 seconds. All right, so we're looking at 2.9 meters per second is the speed of the elevator. Okay, which is about right, okay, for an elevator. And if I want to find the average velocity, okay, well, average velocity is total displacement divided by total time. All right, so that'll be 25 meters up divided by 50 seconds. So we're looking at 0.5 meters per second up as our average velocity. How important is it to include the up on that answer? Yes, without it, it's wrong. Okay, so make sure you have it on there. Otherwise, it is a speed and not a velocity. Okay, questions on how that one worked? All right. Very often you get questions like that on quizzes. Kind of. Okay, give this one a try. We'll finish off with this one. All right, so we got a trip that has 3 parts this time. Not 2, but 3. Okay, a herd of elephants travels north. In part 1 of the trip, the elephants walk for 1.1 hours at a velocity of 3 meters per second north. In the second part of the trip, they walk 7 kilometers south in 1.5 hours. Then they walk at 4.5 meters per second north for another 2 hours. What is the overall distance traveled and the average velocity of the elephants? Okay, so you're being asked to calculate two things. And you do have an issue with units here. You've got time in hours, and you got speed in meters per second. So I would advise converting the hours to seconds. How many seconds in an hour? Everyone wants to say 60. Think again. How many seconds in an hour? 3,600. 60 times 60, right? 60 seconds in a minute, 60 minutes in an hour. Okay,